Hello, this is our first course online, so you are very welcome to visit some selected pages of the complex analysis course of the theory of functions of several complex variables. So we begin with our first lecture with the complex plane. And let me briefly recall the notion of complex number and its basic properties of complex numbers. So a couple xy from R2 is called complex numbers. Complex numbers. When they are equipped with the following algebraic operations. If first, of course, we identify the couples if x1 is equal to x2 and y1 is equal to 1, 2. If and only if. So this is usual rule for points of R2. So the addition of our couples is the usual addition of vectors from R2. And what is most important, and this is the particular property of complex numbers, we have the notion of the product of our couples, which is by definition the following rule: x1, x2 negative, y1, y2, and x1, y2 plus x2, y1. So when these rules are prescribed, we are working with complex numbers. So of course, the first property, the first remark is that if we consider the couples of special form x1, 0, and if we take the sum, then we obtain this couple, which is again of the same form. And if we consider the product using the rule 3, then it is easy to see that we obtain x1, x2, 0. So this means that when we consider our algebraic operations with the couples of the special form, we stay on this set. So this explains why, if we consider here x, you consider here the axis y, axis y. So if we consider the couples of the form x1, 0, x2, 0, their sum remains on this axis and their product remains on this axis. So we do not leave this axis working with these numbers. For this reason, the usual notation for this type of couples is just x, because O, 0, does not change anything, right? So, on the other hand, if we consider the following remarkable couple, I, of the form 0, 1, and if we multiply this couple by itself, that is, if we consider I square, that is 0, 1 multiplied by 0, 1, and we apply once again the rule 3, we obtain negative 1, 0. So our I is here, right? This is just this point. And its product is here. So this is negative 1. And by our convention, this is just -1. Thus, we obtain immediately this fundamental property of complex numbers. There are complex numbers such that the square is equal to -1, which never happens, of course, for real numbers. And one of the main reasons to introduce the complex numbers is to have this property. So from this, we can, it is very convenient to introduce the following algebraic form of a complex number. So if we have a complex number z, this is the standard notation, that is a couple x, y. We can write this couple as a sum of two couples. And then the first couple is just x. And the second couple can be written like this as 0, 1 multiplied by 0, y. Multiplying by y0. So if we apply our rule 3, what we have here, 0y, -1, 0, plus 0, 0, plus 1 times y, right? So we obtain the couple 0y. This is just y, using our convention. And so we obtain, and this is I, right, using this notation. And so we obtain x plus I, y. Thus we obtain this representation of any complex number, which is called the algebraic form of a complex number z. X is called the real part of z, and y is called the imaginary part of z. Okay, so using the algebraic form of complex numbers, of course, we can easily take the sum like this. So we just take the sum of the real parts, and it will be the real part of the sum, and we simply put I as a factor, and then we will see that the imaginary part of the sum is the sum of the imaginary parts. When we multiply two complex numbers, we simply can do the following thing. So we take the algebraic forms and we multiply them using the usual algebraic rules. So just develop this expression, and everywhere where we meet I square, we replace it by -1. So we obtain x1, x2 plus I, y1, x2 plus I, x1, y2, negative, y1, y2, which means that we obtain an algebraic form of the product, which precisely corresponds to the result which we obtain if we multiply the couples x1, y1 and x2, y2 using our multiplication rule. For this reason, nobody uses this multiplication rule 3, which was introduced above. Or if you would like to multiply two complex numbers in their algebraic form, this is the standard way to do it. Just develop the expression using basic algebra rules and replace everywhere where you see I squared by -1. And then you obtain the result. You obtain directly the algebraic form of the product. So this is the standard way to do it. So notation is, if we consider the introduced above set R square with these two algebraic operations. So this is addition and multiplication of complex numbers. The standard notation is C, and we call it the complex plane. The set of complex numbers equipped with these algebraic operations is called the complex plane. Why plane? Because, of course, our complex numbers, so they are points of this plane, and you can consider if you have a point z of type x plus I y, this is a complex number and this is a point of our plane. So now we can consider other operations with complex numbers. One of the very important operations is the complex conjugation. Complex conjugation. So if we consider here a vector z, which corresponds to the complex number z, then z bar is just x negative I y. So geometrically, this is a vector which is symmetric with the vector z with respect to the axis x. By the way, this axis is called the real axis, and this axis is called the imaginary axis, and it is denoted by I times r. Why? Because complex numbers which are located on this axis are of the form I multiplied by y, right, with real y. Okay, so this is the, so z is conjugated to z. But the operation of conjugation is very easy to check it. If you take the sum of two complex numbers and you consider the conjugated number, then the result will be the same as if you take the sum of conjugated numbers, and if we take the conjugated to the product of z1 and z2, the result will be the same as if you take first the conjugations and then you take the multiplications of these numbers. All right? So, by the way, notice that the conjugated number is equal to z. This means that you have this equality, and obviously this happens if and only if y is equal to 0. That is, it happens if and only if our complex number z is real, that is located on the real axis r. Good. So now we need the notion of the modulus z of a complex number z. This, by definition, it is denoted like this, and this is the square root of x squared plus y squared. This is always a real number, of course. This is a real number. Moreover, it is always non-negative, and obviously the modulus is equal to 0, and but only if z is equal to 0. Right? Please note that the modulus of the conjugated number obviously is equal to the modulus of z, and this is important. If you and very often it is useful if we take the product of z with the conjugated. If you take this, you obtain x squared plus y squared. That is the modulus of z squared, right? So this is the properties of modulus. Then we have the following algebraic properties. Algebraic. Of complex planes, C of complex numbers. So the basic properties are, if you take the sum, of course, the permutation is allowed, so this means the addition of complex numbers is a commutative algebraic operation, absolutely the same for the product. Furthermore, the both of these operations are associative. This means, as we know from the algebra, this, right? Right, and we also have the law of distribution. So this means that z1 multiplied by z2 plus z3 is the same as z1 multiplied by z2 plus z1 z3. Right? So this is the basic algebraic properties of complex numbers, which are very similar to the related properties of the real numbers. Well, we also need to discuss the division in C, and as usual, how to define the division. So we suppose that, so let Z1 and Z2 be two complex numbers, and I suppose that Z2 is different from 0. So what is the quotient of Z1 and Z2? Then Z, the quotient, Z1 over Z2, is defined to the following equation: Z times Z2 is equal to Z1. If Z2, as here, is different from 0, this solution exists. This is obvious. Let us just multiply the both parts of this equation by the conjugated of Z2, and we obtain this, right? But this is the modulus square of Z2, so we have also Z2 square, Z1 times Z2 bar, and this is non-zero real number, non-zero because our Z2 is non-zero by assumption, so we just divide and we obtain the quotient which exists and is unique and which can be computed by this formula. All right, so now just a few words about the geometry of complex numbers. So in our plane we have a vector, say Z1. We see immediately that the geometric sense of the modulus is obvious. This is just the usual Euclidean distance from Z to the origin. If we consider another vector Z2, and if you consider Z1 negative Z2, you can view Z1 negative Z2 as Z1 plus negative Z2. So negative Z2 in my picture is here, and so the sum of two vectors is just this big diagonal of a parallelogram. Right, so this is Z1 negative Z2, and we see that the length here is the same as the length, as the length here, right, of this parallelogram, so of this diagonal. the length of this diagonal is the distance between z1 and z2. So this is the same as the length of the vector z1 negative z2. So the modulus of this is just the distance between these 2 points, z1 and z2, right? So here and here, the length is the same. So this means that we can use the models in order to define some geometrically define some subsets of the plane. One of the most important, so examples. The most important example for us will be the unit disk, which are always denoted like this. So this is the set of points of the complex plane such that the modulus of z is smaller than 1. This is obviously the unit disk centered at the origin. Indeed, the condition that the modulus of z is smaller than 1 simply means that the distance from z to the origin is smaller than 1. But this is exactly all points which are in the interior of the unit disk, right? The boundary of the unit disk does not satisfy this assumption because you have equality here. Sometimes we use the closed unit disk when the inequality is not strict. This means that we add to the unit disk its boundary BD, the boundary of the disk, which of course is the unit circle. This is the unit. More generally, we will consider the disks centered at point A and of radius r. R is positive. This is the set of points z of the complex plane, satisfying this condition. Distance from z to A is smaller than r, right? So this is the disk centered at point A and of the radius r. Good. So also we have some useful inequalities. So inequalities, so fundamental inequality. This is the inequality that the modulus of z1 plus z2 is smaller or equal than the sum of the modulus of z1, 2 and bigger or equal than the difference of the modulus z1, negative modulus of z2, and you put the modulus. So this inequality is obvious, right? Because this simply means the classical geometrical principle that the length of the one side of a triangle is always not bigger than the sum of the length of other two sides. And this inequality follows easily with the same proof as in the classical real analysis. All right, so now, we simply use the polar coordinates on the plane instead of the Euclidean ones. So we have complex number then we can consider its modulus r, but we see that the modulus does not determine the position of the point z on the plane. All points with the same modulus run over the circle of the radius r. So we need to, if we would like to precise the position of point z, we have to add an additional parameter. Traditionally, this is the angle phi between the positive direction of the real axis and the direction of the vector z. So phi is called the argument of z. From this triangle, so here we have x, right? And here we have y. And from this triangle, we see immediately, using the classical geometrical principles, that x is equal to r multiplied by cosinus phi, and y is equal to r multiplied by our sinus phi. By the way, if we move to this direction, phi will be positive. If we move in this direction, right, our angle phi is considered as -1. Of course, if we consider these two quantities, we see that the angle, of course, if you know r and phi, then x and y are uniquely determined. That is, geometrically, the position of your point on the plane is determined. But if x and y are given, then you always, of course, you can find r immediately, right? However, there are infinity of angles phi satisfying these equations, right? Because if we add, if phi 0 is an argument of z that satisfies this equation, then you can add any number to pi k with k any integer, positive or negative, and any phi of this type still satisfies these equations, right? This means that the argument of a complex number is not defined uniquely. This is infinite set of numbers of this form. If you know one value of argument, then you have all other values of the argument of our complex number when k runs over z. So this is the set of all arguments of z. So argument of z is not a single number. This is an infinite set of numbers which are obtained by this formula. If you know one value of argument, all other values of argument are obtained by this formula, right? So using this, let me denote this by number 1. So we see that from representation 1, we see that if we write z in its algebraic form, x plus iy, we can replace x by r cosinus phi, and we can replace y by r sinus phi, and we can factorize by r, and we obtain this representation, right, which often is called the geometric form of z. Well, it's very easy to check that if you consider the product of two complex numbers given the geometric forms, then the result in the geometric form will be of this type: R1, R2, that is, you have to take the product of their modules and you have to take the sum of their arguments. This is very easy to check. You take the product of two complex numbers given by the geometric forms, and then you use the usual trigonometric properties of cosinus and sinus, and you obtain it easily. So I do not check it. So this is the very important property of the complex numbers in the geometric form, and this explains why geometric form of complex numbers is so useful So consider the extension of this formula. So now if we consider z in the form r cosinus phi plus I sinus phi, then the power z n is computed by r power n cosinus n phi plus I sinus n phi. So this is the classical model formula. It is important to stress that this remains true for any integer n, positive or negative. You can, if you take n equal to -1, you obtain that z power -1, that is 1 over z, can be computed by 1 over r cosinus. Cosinus is a given function, right? Negative I sinus phi, right? Because sinus is odd function. Good. So also very often the exponential form of a complex number is used. Okay, so the exponential form. So traditionally, it is written, this expression cosinus phi plus I sinus phi is written by exponential I phi, and it is justified because of the rule which I already discussed. So if you take the product, if you take the product of two expressions of this type, this is the same thing as cosinus phi 1 plus phi 2 plus I sinus phi 1 plus phi 2. That is, we have this classical property of the exponential function. When you multiply two exponents, then this is the same as if you take the sum of phi 1 plus phi 2. So we still have this classical property, which explains this notation. A little bit later we will see that there are deep reasons for this notation. All right, and so the last thing which I would like to discuss, this is the roots. Okay, so suppose that A is a complex number, then we consider the solutions of this equation. Power n belongs to n, and n star means that it is different from 0. If A, I suppose that A is different from 0. If A is 0, then of course this equation admits the only solution z is equal to 0. But when A is different from 0, this equation admits exactly n different solutions. In order to understand how to find them, let us represent A in its exponential form, rho times exponential of I theta, and let us look for the solutions of this equation in this form, r exponential I theta. Then by the Moivre form, by the form of Moivre, we obtain the equation rn exponential I n theta. I'm sorry, this is phi. This is phi, of course. This is phi. Exponential of I and phi is equal to rho exponential I theta. And this means that r power n is equal to rho, and phi is equal to theta. But r is just a real non-negative number, so this means that r is equal usual real root from r of degree n, right? And now this equation, and phi is equal, I'm sorry, this means, I forget to mention here that this is exponential of this is equal to the exponential of this. I'm sorry about this. Exponential. And now if we consider this equation exponential e n phi is equal to exponential e theta, this does not mean that n phi is equal to n theta. This means only that n phi is equal to theta plus 2 k pi with integer k. And this means that phi are equal to theta over n plus 2k b over n. Logically, I have to take here all integer k, but in fact, this is the arguments of our roots. If we consider them geometrically, there are just exactly n different angles. Why that? Let us see it on the picture geometrically. So where are our points? So we obtain the points. Zk is equal to n square root of rho exponential e theta over n plus 2k pi over n, right? That's what we obtain. And where geometrically are located these points, the modulus is the same, so we are on the circle of the radius, the root of degree n from rho. So everything is located on this circle. And then, let it be here, will be our point z 0. This means that k is equal to 0. So this angle is theta over n. And what happens when we take k equal to 1? This means that we add here to theta, to our angle, theta over n, we add the angle 2 pi over n. And so we obtain z1, so we add here the angle 2 pi over n. And then we increase k once again, and this means that we turn our point again on the same angle, 2 pi over n. This will be z2, and we continue, and we see that all these points are located on our polygon, which contains exactly n vertex. So this is n polygon, right? And so this is the vertices of this polygon are exactly the roots of our number z. So this is about the roots. All right. So this is essentially all about our complex plane and its algebraic properties. So let us make a pause now, and then we continue with our second area of our topic.